All right. The agenda is to cover Chapter 4, Section 3 today, which is homogeneous linear equations with constant coefficients. So let's get on with it. The nth order linear homogeneous ODE has this form. I must have talked about this a gazillion times throughout the semester, so I'm not going to spend any more time. Okay, homogeneous because the right hand side is 0. And the only thing is, we now are going to introduce something called nth order linear homogeneous ODE with constant coefficients. Okay, what does that mean? These a sub n of x, a sub n minus 1 of x, and all of these, they're not going to be any arbitrary functions of x. They have to be constant specifically. So that changes the thing to a sub n, not a sub n of x. A sub n is just a number, a constant. Similarly, a sub n minus 1, all of these are constants. So those are the kinds of equations that are pretty popular. And so let's learn how to solve equations of that kind. Cool? So I just picked an example, like a sub n is 1 and a sub n is a sub 3, a sub 3 is 1, d cube by dx cube, and so on. Cool? All right. So we will now learn how to find solutions of such equations. We'll use a second order equation to illustrate the process. Okay, that's the idea. So once you understand how this stuff works for second order equations, then you can easily extend it to third, fourth, and other higher orders. Okay, so in a second order case, let's say we end up with ay double prime plus by prime plus cy equals 0. Strictly speaking, I should have said a2y double prime plus a1y prime plus a0y. But, you know, they are the same, like A, B, C are equally arbitrary as A2, A1, A0. Okay. Now, the way you try to solve this is, you first assume y equals e to the mx to be a solution. Now, isn't that a stupid thing? How could you assume let's assume y equals e to the mx to be a solution? Why don't you assume y equals x square is a solution, right? So the idea is some intelligent person somewhere a long time back figured out that this must be the form of the solution for cases like this. Okay, how that person may have come up with, in fact, I cover it in the next section, but here is the idea. So if we assume y equals e to the mx to be a solution, the thing is, we know e is our regular Euler number. X is the independent variable, so we know that also, which means you can set x to be whatever we want. What we don't know is y, and in the right hand side, what we don't know is the value of m. If we can find m, we can claim that we have found a solution. Let me repeat that, please pay attention. To find the solution y, the only thing we need to find is the value of m, or values of m. It could be a plural. Okay, that's the idea. So to do that, let's find out y prime and y double prime and plug them into the differential equation. I can do that because y equals e to the mx is purported to be a solution. So that means these values, when plugged in, must satisfy the equation. And when we do that, we get am square e to the mx plus bm e to the mx plus e to the mx. Looks like I can factor out a e to the mx. When I do, I get am square plus bm plus c. E to the mx times am square plus bm plus c equals 0. Okay, let me put your minds at ease. I have split this into part A and part B. The part A covers a whole bunch of theoretical aspect of it. Why, what to do, what do you end up with, and all that. And in part B, I will actually solve problems. So if you want to just relax a tad here and absorb as much as you possibly can, that's okay. Okay, because in the next part, I'm going to actually apply and show you what all we need to do to solve problems. All right. So after this, can I say this implies am squared plus bm plus c equal to 0? Can I do that? What I'm asking is it not the case that if a times b is equal to 0, then either a equals 0 or b equals 0? So that means either e to the mx is 0 or this stuff is 0, which means, of course, both could be 0 is a different case. That's also automatically understood. But the thing is, I don't seem to say e to the mx could be 0. I just cavalierly said this must be 0. Why? Because e to the mx is not going to be 0. Right? Only when x approaches negative infinity, this quantity approaches 0, but otherwise no. So that means the only way the product could be equal to 0 is if the stuff inside the parenthesis is 0. Cool? All right. So we end up with am squared plus bm plus c equal to 0. Wait a minute. What is this? What are we trying to do? Let's go back. We are trying to find the solution of this differential equation. And to do that, we said assume y equals e to the mx to be a solution. We can claim that we found the solution the moment we find the value of m or values of m. Now notice, are we in a position to finding the value or values of m? Yeah. Is a known quantity? A, B, C, are they known quantities? They are, because you would know the differential equation, which means you would know these coefficients A, B, C of the differential equation. So once you know that, all you have is a quadratic equation. We know how to solve quadratic equations. So that will give us m's, the values of m. And pretty much that means we know the solution of the differential equation itself is. Okay? And this equation am squared plus bm plus c equals 0 is called the characteristic equation of the differential equation. Some people call it transcendental equation, transcendental or characteristic equation of the differential equation. Okay. So let me try to walk through this whole thing. What did we want to do? We wanted to find the solutions of the differential equation. Did we do that? We assumed y equals e to the mx to be a solution and got am squared plus bm plus c equal to 0. Can we find the values of m? Yes, by solving the quadratic equation. This is what I was talking about. Suppose the two values of m turned out to be, say, m1 equals 2, m2 equals 3. What does that mean? What is the solution? Well, what are the two solutions? You know m to be 2, that means y equals e to the 2x is one of the solutions. Is there another solution? Yeah, corresponding to m2, which is equal to 3. E to the 3x is the second solution. Excuse me. That's the idea. So everything hinged on finding the values of the m, and once you got that, e to the 2x and e to the 3x are the solutions. The thing you have to ask at this stage is, wait a minute, are they linearly independent? Again, that linear independence, the stuff comes up, right? And so, are they linearly independent? Yes, it turns out e to the 2x and e to the 3x are linearly independent. So we can be confident that yes, we found two solutions to this second order differential equation, homogeneous equation, like we are supposed to. Great. One caveat though. We can claim to have found two solutions if the two are linearly independent. Well, is there a case where the two will not be linearly independent? Yeah. So we'll cover that in just a second. So I wanted to find out for myself, hey, how did someone know to assume this? I didn't know the answer for a long time. Just recently, I said, wait a minute. Can I answer that question? Why someone came up with that? And here is the thought I got. I said, what about a first order equation with constant coefficients? Instead of second order, ay double prime plus by plus ay equals 0, what if it's a first order with constant coefficients? Ay prime plus by equal to 0, right? That's what I wanted. I wanted to check. And boy, my joy knew no bounds when that was the trick. So ay prime plus by equal to 0. We know how to solve that. I could have done maybe I did do integration by separation of variables technique, right? And so I did that, and the solution turned out to be e to the negative bx over a. Or for that negative b over a, I just thought of it as some m. So sure enough, for the first order with constant coefficients, we do get a solution of the form e to the mx. So maybe as it stands to reason that for a second and third and higher order equations, you could assume e to the mx to be a solution, right? I thought, and sure enough, that seems to be the idea. Okay, to be assumed solution, we got the characteristic equation, and m equals negative b plus or minus square root of b square minus 4ac over 2a. At this stage, if some of you who learn to sing that song wish to sing that song, please go ahead. Usually in a regular classroom, I would have some volunteer who would sing that song. I can't. I don't know it that well. And so this has two solutions, m1 and m2. And y equals e to the m1x and y2 equals e to the m2x. Those would be the two solutions. Now the problem is, could m1 equal m2? Why am I interested in that? Why do I care whether m1 equals m2? Oh, that is because if that were to be the case, then e to the m1x and e to the m2x are not linearly independent. So you couldn't really claim that you have found two solutions. That's the idea. Have we found two linearly independent solutions? If the answer is no. So that's why we have to do three different cases and solve this problem. The first case is when the discriminant, what is that b square minus 4ac stuff in this square root, when the discriminant is greater than 0, then the two solutions m1 and m2 of that characteristic equation are real, and they are guaranteed to be unequal, because one would be negative b plus square root of b square minus 4ac, and that square root of b square minus 4ac will be some non-zero number, and then you would have negative b minus square root of b square minus 4ac all over 2a. So the two things would be real and unequal, and so in that case, yes, e to the m1x and e to the m2x would be linearly independent solutions. Okay, and also the set of linearly independent solutions y1, y2, y3 all the way up to y sub n on I of this differential equation with constant coefficients, nth order, linear, homogeneous with constant coefficients, is called as the fundamental set of solutions on I. Okay, this way when you find these solutions e, y1, y2 and all that, they are called the fundamental set of solutions on I, provided they are linearly independent. Okay, and another one, if you find those fundamental set of solutions, from that you can form what is called a general solution. And a general solution would be just a linear combination of each of those solutions. That's a fancy way of saying a general solution y is equal to some constant c1 times the first solution plus some other constant c2 times the second solution, and so on, all the way up to the nth one. Okay, that's the idea. So we are usually interested in both the things, the fundamental set as well as the general solution. Okay, so when we found e to the m1x and e to the m2x as two solutions, they formed a fundamental set. And from that, we can write the general solution as y equals c1 e to the m1x plus c2 e to the m2x. Cool? Boy, I'm boring the heck out of you, am I not? I'm sorry, guys. I mean, there's nothing I can do. I have to cover all of this stuff. So please bear with me. If it's a regular classroom, I would stop and tell a joke just to get people's mood back into this thing. But this is a recording and I don't want to do all of that. Okay? So please bear with me and let me run through this. And when we get to problem solving, things would be infinitely more clear. Okay. All right. For case 1, when discriminant is greater than 0, we have two solutions and we have this to be the general solution. However, when the discriminant is equal to 0, we have m1, m2 to be real and equal, right? Both the solutions would be negative b over 2a. First m1 equals negative b over 2a, and m2 will also be negative b over 2a. So that is a problem. And so we have only one solution, e to the negative bx over 2a. We don't have a second linearly independent solution. So what do we do? Right? Let me repeat what the problem is. We have a differential equation of the kind ay double prime plus by prime plus cy equals 0. And we found one solution. We don't know the second solution. What do we do? How do we find that second solution? Well, in 4.2, isn't that what we did? Given a differential equation and one solution, did we learn how to find a second solution? Guess what? We will employ that technique. Okay, and so here we have the differential equation and one known solution, and so p of x divided throughout by the coefficient of y double prime, and so p of x is b over a. We need to find negative integral of p of x dx, and that turns out to be this. And what's the next step? E raised to negative integral of p of x dx. We found that, divided by the first solution, and lo and behold, this turns out to be just 1. And so we just get x. What is x? That integral thing. So what is y2? y2 is y1 times this integral. So that means y1 times x. So y2 is nothing but x times y1. Oh, that made life easy. Right? Can you see that life has been made very easy based on this one? Here is the idea, folks. When you get that am square plus bm plus c equal to 0, the characteristic equation, and you find that b square minus 4ac is 0, that is, the two roots are equal. Let's say one root is 2. 2, 2 are the two roots. Then e to the 2x is one solution, and according to this, x times e to the 2x is the second solution. That's it. All you need to do is multiply that by x, and you got the second solution. Okay, As simple as that. So in this case, e to the mx is one solution, x e to the mx is the second solution, and the general solution itself is a linear combination of this. That is, take the first guy and multiply by c1, plus take the second guy, multiply by c2. That's your general solution. Cool? All right, one last case is, what happens if b squared minus 4ac is less than 0? That means you have a square root of a negative number. That leads to complex and unequal solutions for the characteristic equation. And so, let's say those are of the form alpha plus or minus I beta. What? Yeah, they are guaranteed to be complex conjugates. Negative b over 2a plus whatever that square root of negative square root of b squared minus 4ac would be some kind of some I times something. Divide that by 2a and that's what your beta is. So guaranteed that in that case, the two solutions are of the form alpha plus I beta and alpha minus I beta. So guess what? So that means the first solution of the differential equation is e raised to alpha plus I beta times x. y2 is e raised to alpha minus I beta times x. And because these two, the exponents are unequal, these two are linearly independent solutions. Cool? And so the general solution happens to be some constant d1 e raised to the first d1 times the first solution plus d2 times the second solution. Okay. Why did I say d1? I usually say c1, right? Well, there is a reason. Can I factor out a e to the alpha x from both the terms? Yep, because this is e to the alpha x times e to the I beta x. That's what allows me to factor out e to the alpha x. When I do that, e to the alpha x times this d1 e to the I beta x plus d2 e to the negative I beta x is what I get. But then there is something called an Euler's formula, which says e to the I theta is cosine theta plus I sine theta, and e to the negative I theta is cosine theta minus I sine theta. Okay, so I apply that to this part. I replace this e to the I beta x with a cosine beta x plus I sine beta x, and e to the negative I beta x with cosine beta x minus I sine beta x. And when I do that, and I rearrange the terms, factor out a cosine beta x from this guy and all that, and replace this d1 plus d2 with a c1 and id1 minus id2 with a c2, this is what ends up being the solution, general solution. All right. Now, if you didn't pay attention to this whole thing or didn't get a whole lot up to this point, don't worry about it. Only thing is, I want you to focus on the summary that I'm about to give you. This, now pay attention, because I just want to summarize the whole thing. If you can remember the summary, I'm a happy man. Given this differential equation with constant coefficients, the characteristic equation is automatically am squared plus bm plus c equal to 0. And find the roots of that characteristic equation. If they are real and unequal, like 2 and 3, then the fundamental set of solutions would be y1 is e to the m1x and y2 is e to the m2x. And the general solution is a linear combination c1 e to the m1x plus c2 e to the m2x. On the other hand, when m1 equals m2 equals m, like the roots turn out to be 3 and 3, in that case, the fundamental set of solutions are e to the mx and x e to the mx. Remember that you need to multiply by x. X e to the mx is the second solution. Cool? And the general solution is a linear combination of these two guys. c1 e to the mx plus c2 x e to the mx. Cool. Finally, when the roots are complex, that is alpha plus or minus I beta, then fundamental set of solutions would be e to the alpha x cosine beta x and e to the alpha x sine beta x, and a linear combination is the general solution. You must remember this this summary. You must remember what to do in each one of these cases. So the last one, notice this form. Alpha plus or minus I beta are the complex roots. Then e to the alpha x times c1 cosine beta x plus c2 sine beta x is the general solution. Alright folks, that's it for this one.